Here's what we're talking about today. We are talking about parametric functions, also known as vector functions. So I hope you haven't forgotten everything you ever learned about vectors, or else this is going to be a little bit more confusing. All right, now, the biggest thing I said about vectors is that they were independent of location, and that's true. But we're going to lock vectors down to a single point to start with. It's going to be a little bit confusing, but I'll show you what I mean in a second. We're going to start with an example. Imagine a point on a line, and that line is parallel to a given vector. How could we describe that line? So there's a line, it's got a point on it, and this line is parallel to some vectors, because every vector has a slope that doesn't change. Okay? So for example, if that point were 2, 2, that's the point I have graphed right here, right? I've got that sitting here. Okay. What if it passed through 2, 2, and the line was parallel to, I'm just going to make one up, the vector -1, 3. Okay. Here's how we might talk about that line. So we're looking for a line that passes through 2, 2, and it's parallel to this vector. Notice the difference. Parentheses for the point, brackets for the vector. You have to go back to keeping track of those. I need to know by how you write it that you know the difference between a point, a location, and a vector, which is not a location, can be anywhere. But we're going to draw this vector starting from this point. We're allowed to do that, right? We can start a vector from anywhere. So this means this -1 is our horizontal component, so that would mean 1 to the left. And then this 3 is our vertical component, so that would mean 3 up, which we got there. So I'm going to go over 1, up 3, and that's the vector I'm talking about. Does that make sense? Okay, good. The instructions didn't say to talk about so we're imagining this point on a line parallel to a given vector. Okay, here's the next challenge. There's a line going through here, but this isn't the line. That's the vector. I want to describe this line. There's a couple ways I could do this. I mean, this vector, it's kind of like a slope, right? Let's move this thing that way. Keep it over there. This is kind of like a slope. Like the 3, this could be the rise, the -1, that could be the run. I just graphed a line with a slope of -1 in a way. We could figure it out eventually, but there's another way to describe this line. All right? Well, first off, what if I started adding vectors to this? Or what if I doubled this vector? What would that look like? If I said start at 2, 2, and what if I'd said parallel to 2 times -1, 3? Where would I have wound up then? How far to the left would I have gone? 2, -2, 2 to the left, right. And how far up would I have gone? 6. Okay, so let's go over 2. And then from here, so this is at 2, go over 2, up 6 would be 8. All right, so I'm still on that line, right? What if I'd said, okay, what if I had said start at 2, 2 and go parallel to -1 times the vector -1, 3? What would that tell me to do?
Right, 1.
Yep, left would become right, very good, and up would become down, okay. So that would be to the right 1, and down 1, 2, 3 would take me to -3. Whoops, I can draw that a little better than that. Looks like we're still on that same line, right? Okay, so in other words, one way to describe this line, without going back to Algebra 1, slope-intercept form and all that, I could describe this line as start at the point 2, 2, and add this vector -1, 3 to it. Kind of like adding vectors. Add the 2 to the -1. That's how we got to this point of 1. Add the 2 to the +3, the y value to the 3. That's how we got up 5 from there. I'm sorry, up 3 from there. We wound up at 5. But then we also didn't just start at the point and add the vector. We started at the point and added double the vector. We started at the point and added the opposite of the vector. This is understood to be the number 1, correct? 1 times anything? So basically, I started at the point and I added 1 times the vector, then 2 times the vector, then -1 times the vector. I start at the point and I added, I'm going to call these numbers t. T is my parameter. I'm going to call it t. 1 is an example of t, 2 is an example of t, -1 is an example of t. So I'm going to describe this line as starting at 2, 2, add t, some multiple of this vector. And if t is equal to 3, I'll wind up here, but on the same line. If t is equal to -2, I'll wind up down here, but still on the same line. If t is equal to 1/2, I'd wind up right in the middle of this vector. So should this describe a line that starts at 2, 2 and stays parallel to this vector -1, 3? Should work. All right. Now, this is a powerful way to describe things, but not just because it's kind of cool and visual and all that, but we can split things up a little bit. We can talk about the vertical components separately from the horizontal components. What letter do we usually use to talk about things that are horizontal?
H.
H, good, yeah, okay, right, when we're shifting functions. But okay, but in general, what do we talk about? What else do we use for horizontal? X. And what do we use for vertical? Excellent. Another way to find points on this line is the X points are the ones that start at 2, and then you take t and multiply it by the horizontal, the x component of your vector. This will get you x coordinates on this line at various t values. Then we take the y, our horizontal parts. Our y values are all going to be 2, we're going to start at 2, plus t, and here we only care about the vertical part, so that'll be t times 3. So we call these parametric equations. The parameter is t, you don't see it. A parameter is something you don't see. Dimensions, x and y, you see dimensions, you don't see parameters. But if you want to find all the points on this line, if you want to make a table and plug in like you did in Algebra 1, you would find x's by plugging them into 2 plus -t, 2 minus t, and you would find y's by plugging them into 2 plus 3t. If we've done this correctly, then any number you pick for t will give you a point on this line. Put in 0 for t, you'll get 2, 2. Put in 1 for t, you'll get 2 minus 1, which is 1. You'll get 2 plus 3, which is 5. 1, 5, that's this point here. That's how we got along that vector. Okay, so we'll talk later about the advantages to using parameters as opposed to other things. But this is how you find a parametric equation of a line using vectors and a point. We'll see how well I did in a second. I'm going to save this for the written notes. That picture, because I'm going to have to make it go away now. Let's see how we did. That's the point 2, 2, 2, right? And the vector we picked was -1, 3, right? How's that compare to my line? Did I have 1, 5 on my line?
Yes.
And did I have 0, 8? I hope so. 3, -1. So what I did is I set this up to, from the origin, you go up to 2, 2. And then this point here is what you get when you add one vector. When you add another vector, when you subtract vectors, you go this way. This is a way to show, I have it set up to show like the first 3 vectors, I think, in each direction. This is another way to look at a vector form of a line. And if you change the vector that the line's supposed to be parallel to, you get a different line. Oh. This could describe starting at 2, 2 and only going left and right. You can picture that as a vector that goes, looks like I've set this up to go 10 left and 10 right, but stay at the same height. Oh, I did. I can switch the direction on this. Oh, the vectors just switched. So you could draw those as vectors on it. I'll set this on the topic page if it's helpful, but you can also move this point around. You can start at a different point, but notice the slope of the line isn't changing. If I go back to my original vector, what did I start with, for example? -1, 3? Does that look right? If I start somewhere other than 2, 2, I'm still parallel to that vector 1, 3. Does that make sense as an idea of what we're doing? Okay. We're not going to talk about the why yet. All right, that comes later. We'll start with the how. Over the next few days, we'll talk about the why. I'll give you a quick hint. The most common version is you have t stand for time. Like when you graph a line, y equals mx plus b, you don't know when the point is there. You guys have been graphing intersecting lines for 3 or 4 years now, right? What if you were actually talking about colliding objects? Doesn't it matter when the objects collide, not just where? You know, if you have parametric equations, you can start talking about that. T could describe the time at which an object is at this point. So that's important. Go back to that first example. If t were time, then at 1 second, the object would move from 2, 2 up to 1, 5. So parametric lines have to have direction, but that's the most common use of it, parameter and time. All right, I think I'm done with this part. So let's move on to what you guys are going to do by hand. Oh, let's get a graph going. Okay, so let's put the graph in here. And this example is not the one I wanted. Let's go back to the beginning and go in order. All right. So, write a vector describing a line passing through the point 1, 4 and parallel to the vector 3, -2. All right, here is 1, 2, 3. That's 1, 4, correct? All right, now from that point, I'm going to draw a vector. You're going to wish you had this bright link for your homework. I'm going to draw a vector that goes 3 to the right and down 2. That's my first vector. This is what's happening when t is equal to 1. You are at this point. All right. What would happen if t were equal to 2? What would I do then?
Go right. 6.
Oh, from my starting point, right? From this point, I'd go right 3 again and down 2. But you're right, Harrison. From the starting point, I'd go over 6 and down 4, right? So if we were talking about time, if it was at our parameter, this is what's happening in this situation at 2 seconds. If this were time and you were wondering what this object was up to 1 second before you saw it, well, if it was following this pattern, if I put in a -1 for t, I'd go backwards 3 and up 2, And I would know, assuming this pattern held, that this is what was going on at t equals -1. I could find those points, right? And this was my point 1, 4. They didn't ask that. They said, write a vector equation describing the line. Well, the vector equation is, whoops, I must use the wrong notation. We start at the point 1, 4 plus t times the vector 3, -2. And if you want to make these parametric equations, x would equal, well, x. X is, well, I don't like that highlighter color. Right now, anyway. X is the horizontal parts. These are the horizontal parts, right? So x is going to be 1 plus 3 times t. 1 plus 3 times t. Does that make sense?
Yeah.
Okay, and then the vertical parts, 4 plus -2 times t. I would write that as y. The vertical part is 4 minus 2t. And these are my parametric equations for this line. This one up here, that's my vector equation. Does that make sense? Any quick questions just on this part? No? Okay. Let's take a look at another example. Okay, they give the order a slightly different order. Find the parametric equations for a line parallel to the vector q, which is 6, -3, and passing through the point -2, 4. Then make a table of values and graph the line. All right. The vertical is, it starts at an x value of -2, and it goes up 6 every time t increases by 1. I'm sorry, I just said that wrong. That's the horizontal, right? The horizontal starts at x equals -2 and goes left to right 6. The vertical starts at -4 and goes down 3 or up 3, depending on what x or y is doing. So this is going to be, my parametric equation will be x equals start at -2 plus 6t. Is that correct? Double check me. And then my y is going to start at -4 and be minus 3t. Double check me, am I good? All right, here's what the table of values looks like. It's kind of going back to Algebra 1 a little bit. Remember doing this when you first graph like lines or parabolas? Now, here are my dimensions. That's supposed to be a highlighter. Here's my horizontal dimension, my vertical dimension, and then there's my parameter, which you can't see on your graph, but is there. It's like a puppet master. So when t is -2, put -2 in for t, what should I get for x?
-4?
No, -2 times 6 is -12, right?
-14.
-14, I hope. All right. Put -2 in for y. -3 times -2 is +6. -4, 2. Does that look right?
Yeah.
Okay, I feel good about that. -1, -2 plus 6 times -1, -8. -4 minus 3 times -1 is +3. Is that -1?
Yes.
Double check me. Okay, 0. Just put in -2, -4. We're good. 1. -2 plus 6 times 1, +4. -4 minus 3 more, -7. And 2. -2 plus 12, 10. -4 minus 6, -10. How'd I do? Because I'm going to be really embarrassed if these points are not in a line. All right, let's graph these points, make sure they're in a line. There are other parametric shapes besides lines, but we're not dealing with them yet. Do I graph this -2 in any way? No, just graph the x's and y's. -14. All right, I'll make my scale 2 to 1. So 1, 2, 3, 4, 5, 6, 7. Up 1. This will be my -14, comma 2. So -8 will just be there, and -1 would be down here, correct? And then, so -2 would be there, -4 would be there. They still look like they're in a line? Okay, +4, -7, 2, 4, 6, 7. And +10, 1, 2, 3, 4, 5. 1, 2, 3.
It's 4, -7.
Thank you, I mislabeled it, didn't I? Thank you, Mickey. Excellent. No reason to make this any more confusing than it has to be. Is this 10, -10? Did I do that correctly? Hopefully. Let's find out. Easy enough to check. Did I get a line?
Yep.
All right, well, it was supposed to be a parametric line, so that's a good sign. All right. This is... Love it when it does that. Okay. Cheap trick here. Very cheap trick. Write parametric equations of y equals -4x plus 7. They didn't give us a vector. They didn't give us a point. Okay? This is ridiculous. Are you guys ready for this? This is the easiest way to do this. If the directions just say write parametric equations, first off, don't underline it in a line. Not at all what I meant to do. This is what you do. Are those parametric equations that would mean the same thing as that? Yeah, the only difference is these would have a direction. If you graph this, you have to indicate a direction. And the direction is always in the increasing order of t. Now, it didn't say to graph it. But this is a good place for me to make this point. We can graph this a couple of different ways. I'm going to graph this at first, sort of the old style way. I'm going to go up to 7. 1, 2, 3, 4, 5, 6, 7. And then I'm going to go down 4. 1, 2, 3, 4, and over 1. So here's the line, right? Okay? A parametric equation always has a direction, and direction is always in the order of t increasing. Direction is always in the order of t increasing. So this line, I'm not going to put the usual arrows at the end. This line looks something like this. And it goes, the line does go on forever, but you always have to indicate in what order, say, something moving along this line would be moving if it were in the order of increasing t. So when t equals 0, what's going on? Where are you when t equals 0? Where are we? 7 on the y-axis. Perfect. When x equals t, so when t is 0, x is 0, put a 0 in here, we're at 7. Where are we when t equals 1?
1.
X is 1, and y is?
3.
3, very good. -4 times 1, 3, okay. So at 1, here's t equals 0, here's t equals 1. The direction of this parametric line is down and to the left and only down and to the left. You don't have to put as many arrows as I just did, but full credit on graphing anything in parametric form, you must include these arrows. Otherwise, you haven't given me all the information I need. Does that make sense? The directions, by the way, if this is all the directions on the homework, then literally you're done here. But I want to take this as a chance to say this. Parametric lines, I know I showed vectors going in both directions originally, just to kind of show where this comes from. But when you finally graph your parametric line, you should put the arrows just going in the direction of increasing t. And we'll look at parametric curves later. Here's the example I accidentally started on. Write an equation in slope-intercept form of the line whose parametric equations are x equals -5 plus 4t and y equals 2 minus 3t. This one's slightly trickier. Slightly trickier. Here's what we're going to do. X equals -5 plus 4t, right? So then x plus 5 equals 4t. I can add 5 to both sides, correct? In fact, I can even say that t is equal to x plus 5 over 4, right? Okay. Y then is 2 minus 3 times x plus 5 over 4. Remember substitution? If t is the same thing as x plus 5 over 4, then anywhere I see a t in the original, I can put x plus 5 over 4, right? Are there any t's left in this equation now? Now, so what you do is you use substitution. You use substitution and you eliminate the parameter. That's what we just did. It's called eliminating the parameter, and we just did it. Technically, we followed the oh, wait, we missed something. If all it said was eliminate the parameter, we could stop here. Why can't I stop here?
Because you have to write it.
Yeah, the direction said slope-intercept form. I'm not done yet. I've got some algebra in my future. So y equals 2 minus, I can take that 4 out if I want and write it like this. Still not there. Fractions will be a little bit ugly. 2 minus 3/4 x minus 15/4. Did I distribute and multiply correctly there? Okay. So y equals -3/4 x plus 2 minus 15/4. 2 can be rewritten as 8 over 4, correct? Common denominator, what's 8 minus 15? -7. So y equals -3/4 x minus 7/4. If we've done our algebra correctly, then this is where we're done. So that covers taking parametric equations from how to create them from a point and a vector, how to graph them, how to create them from a line and slope intercept form, and how to take them and put them back into a line and slope intercept form. You guys think you can handle that? I have faith in you all. There it is. If that audio sucks because it was using the microphone over there, I will sync it up with this audio.